Now it is visible?
No, sir.
No.
No, sir.
Not visible.
No, not visible.
Yes, sir. Yes, sir.
Right. So we will discuss selective harmonic elimination and hybrid PWM technique for this cascade edge bridge inverter. So we already discussed this in previous classes, right? So now, so in this lecture, we will. So what is the exact switching instant, right? What is the exact switching instant to obtain this kind of staircase waveform, so which is operated at a fundamental frequency? Okay, so this is known as staircase modulation or selective harmonic elimination for cascade edge bridge. Right. So let us assume that there are 5 H bridges. There are 5 H bridges per phase. So each is fed from a DC source of VDC. So each H bridge is fed from a DC source of VDC. So let us assume that this is the output voltage that generated by the first H, and this is the second H bridge, and this one is the third H bridge, and this is the fourth H bridge, and this is the output that generated by the fifth H bridge. Right. So assume that this is operating at this is switched on at θ1 instant. Right. So obviously to symmetry, so this is operated pi minus θ1, and this is θ2, this is θ3, and this is θ4, and this is θ5. Right. If we have n H bridges, right? For example, if we have n H bridges, so how many levels you can get in the line in the phase voltage? You will get 2n plus 1, right? So where n is the number of H bridges per phase. So
Sir, you are not audible, sir. Hello.
yeah, my voice is audible now.
Yes, sir. Yes, sir.
Yes, yes, sir. Yes, sir. Yes, sir.
So today it's not going well. Okay. Okay. So this is the output that produced by the different H bridges. So let us assume that we have n number of H bridges per phase. So you will get an out in the, you will get 2n plus 1 levels in the phase voltage, right? So that means you have angle theta n, right? This is θ1, θ2, θ3, θ4, θn. Okay. So θn is the output angles, that means angle that produced by the nth H bridge, right? So if you have this case, right? So if you have this case, so you ultimately got this staircase waveform, right? So this staircase waveform you can write in terms of Fourier series. You can write in terms of Fourier series, So that Fourier series is something like this. Right. Right. So this is the output voltage that produced. Right. So this is the output voltage that produced. So this is equal to 4 VDC by pi into sigma cos n theta 1, right? Cos n theta 1 plus, this is under, plus cos n theta 2 plus cos n theta 3 and so on up to cos n theta capital N. So where this capital N is the number of cascade H bridges so that are connected in cascade, right? Okay. So into, not over, into sine n omega t by n. Clear? So this is the Fourier representation of that stepped waveform. This is the Fourier representation of this waveform. This is the Fourier representation of this waveform. So if you have n H bridges in the cascade. So we already discussed when we have studied the space vector, or not space vector, selective harmonic elimination. We already discussed this, right? Okay. So here, if you consider it is a per unit, right? So per unit means we can assume that VD is equal to 1 per unit. We assume that the VDC is 1 per unit. So this equation can be written as, or its constant can be written as, so these are the constants. So h of n, so these are the constants. We can written as 4. So this is n, right? So 4n pi into cos n theta 1 plus cos n theta 2 plus and so on cos n theta capital N, right? So this is the coefficient of nth order harmonic, right? So this is the coefficient of nth order harmonic. So this is, you have h1, h2, h3. So that means n equal to 1, 2, 3, 4, right? So similarly, you have this h1. So if n is substitute n equal to 1, so you will get h1, h2, h3. Similarly, h2. So you need to substitute n equal to 2. So these are the coefficients, right?
So,
Yes.
sir, yeah, there is a summation above, right? Above, right?
Not audible.
Sir, there is summation, one summation in the above expression.
I'm not clear what you're saying.
Yeah, is it capital N or small n? Or small n? Summation.
This is capital N. Okay, so n will vary from 1, 2, 3, and so on, right? Okay, it's up to infinite. So where this capital N, okay, so this is the cascade number. Okay, so that is a number of H bridges in cascade. Okay, the number of H bridges in cascade, right? Okay, so here this angle already we have theta and angle, right? So this is the first one, first H bridge, second H bridge, and this is nth H bridge. Okay, since it is a Fourier series, so the series will change from that is 1 to infinite, right? Yeah. So these are the coefficients.
Yes, sir.
So normally, so if you have 1, 2, 3, and 4, right? So for even numbers, so its value is 0. For even numbers, so its value is 0. So therefore, the series will vary from 1, 3, 5, 7, and so on. So the series will vary from 1, 3, 5, 7, and so on, right? Clear? Okay. So now our objective is, for example, consider the capital N, so that is equal to 5. So consider capital N, so that is equal to 5. That means 5 H bridges are in cascade. So now we need to define the modulation index MA. Okay, we need to define the modulation index MA. Right. So let us assume that the V0 is the output voltage, right, or the reference voltage, so that produced, so that is VL star, for example. So this is the reference voltage that must be produced by the inverter, okay, or the inverter output voltage. This is the inverter output voltage, okay, and we have this VL maximum. Okay, so this is the maximum voltage or the peak voltage, so that produced by the inverter. So this is the peak voltage produced by inverter. Okay, so what is the peak voltage that produced by this inverter? If you have n equal to 5 and each one is VDC, what is the peak voltage that the inverter can produce? What is the peak voltage that inverter can produce? So in this case, right, for example, in this case 5, so what is the peak voltage here? This is 5 VDC, right? So 5 VDC is the peak voltage, right? So in this particular case, so what is the voltage that produced? So that is n VDC. Okay, so this is the peak voltage that produced by the inverter. Okay, so MA is defined as the output voltage that you required by the peak voltage. Okay, so that means MA equal to, so VL star, that is the output line voltage you require, output voltage you require, and so this is n times the VDC. Okay, n times the VDC. Clear? So that means this output voltage, so this n VDC into this MA. So this n VDC into MA. Is clear? So this is the output voltage, that is the output phase voltage you required. Okay, this is the phase voltage you required. Clear? I think this is somewhat confusing. I remove this L. So now it will be clear.
Actually, what is that
So this is the
restart,
output
sir?
voltage. I will write P0. Okay, so this is the output phase voltage that you required divided by the maximum voltage that produced by the total number of H bridges. So that is n times the VDC. Is clear? So now this is the output voltage that produced, that is the NVDC into MA. Okay, so let us assume that you have n equal to 5, right? So n equal to 5. So that means how many angles you will get? So theta 1 to theta 5, right? Yes, you will get theta 1 to theta 5 angles. Okay, so in this we can eliminate certain harmonics. So in this process we can eliminate certain harmonics, right? So anyway, the third, we have this list, right? We have 1, 3, 5, 7, 9 and so on, right? So anyway, this is 3-phase, right? So this 3-phase star connected, so therefore this third order harmonic, so by default it is eliminated, right? Similarly, this 9th order harmonic, so by default it is eliminated. So we have this 11, 13, 15. So this 15 also by default, so it is eliminated, right, in the line voltages. Okay, so therefore you can eliminate certain harmonics. So let us assume that I want to eliminate this 5th order harmonic, 7th order harmonic, 11th and 13th order harmonics. Okay, I want to eliminate this 5th, 7th, 11th and 13th order harmonics in the output voltage. Okay, so we already discussed that. So along with that, we need to control the fundamental. So this is the fundamental, and these are the harmonics that need to be eliminated. So these are the harmonics that need to be eliminated. Okay, so we can write the equations. For example, so this is the 5th order harmonic, right? So what is the coefficient for the 5th order harmonic in this? So H5, so that is the coefficient for the n equal to 5 right now, 5th order harmonic. So 4 pi, 5 pi into cos n theta 1, cos n theta up to cos, that means n it is pi theta 1, pi theta 2, up to plus cos phi theta n, right? So if you substitute that, so what you will get, so this is the coefficient, so corresponding to harmonic 5, right? So H5, so you will get cos phi theta 1, right? Something you have there, right? So what is the coefficient? So 4 by n pi, right? So 4 by n pi. So that means it is 4 by n pi. So that is 5 pi. Cos phi theta 1, cos phi theta 2, is cos phi theta 3, is cos phi theta 4, plus cos phi theta 5. Okay. So this is the coefficient of this fifth order harmonic, right? So this entire thing we want to eliminate, right? So therefore equal to, or make it equal to 0. Clear? Similarly, H7, want to eliminate H7, right? So H7 coefficient also we need to eliminate to 0. So that means this is 4 by 7 pi. So we will get cos 7 theta 1, cos 7 theta 2, is cos 7 theta 3, and so on, cos 7 theta 5. So this is also equal to 0. Similarly, H11 and H13. So 4 by 11 pi, and this is 4 by 13 pi. So you will get cos 11 theta 1 up to plus cos 11 theta 5. So this is 0. And we have this cos 13 theta 1 plus and so on, cos 13 theta 5 is 0. It's clear? Okay. So we are equated, so all the coefficients of the harmonics that we want to eliminate, so that to 0. So now we need to control the fundamental voltage. So we need to control the fundamental voltage. Fundamental voltage is H1. Okay. So the fundamental voltage is H1, right? Clear? So now how it is controlled? So this is not 11. It's 4 by 5, right? Okay. So what is the fundamental voltage? So in this is the fundamental, right? 4 by pi into cos theta 1 and so on. So that is the fundamental. So we have this 4 by pi cos theta 1, right? Plus cos theta 2 plus cos theta 3 plus cos theta 4 plus cos theta 5. So what is this value? So what is this value? So what is the value of this one?
MA.
Just MA or something is there. This is the output voltage of entire thing, right? Okay. So output voltage we derived. So this is the one, right? VDC, right? So VDC we already assumed that this is 1 per unit, right? So therefore, so this is 10 times MA. Okay. So obviously this VDC will be there. Okay. So this VDC will be there, but we assume that so this is 1 per unit, right? Okay. So therefore we can get that. So therefore this is equal to n times the MA. Clear? Is clear? Okay, this is the output voltage of the fundamental, output voltage of the fundamental, right? So this is the desired output voltage. Okay, so now we have these 5 equations. So if you solve these 5 equations, you will get the different angles, right? So in this particular case, if I solve this one, you will get theta 1, so that is around 6.57 degrees. Okay, so this theta 2, so you will get something like this 18.94 degrees, and theta 3, we have this 27.18, theta 4, 45.45, and this theta 5, okay, 52.24. Right. Clear? So that means, so this is the firing pulse, right? Theta 1, right? So this theta 1, this is the firing pulse, right? theta 1 is 6.57, right? So obviously this is the other one is 180 degrees minus theta 1, right? So this is 180 degrees minus theta 1, this is 180 degrees minus theta 2. Similarly, this is 180 degrees minus theta 5. Okay, so we need to generate these kind of pulses. Okay, so we need to generate these kind of pulses so that you will get a harmonics. This means the output voltage like this. So in that, so harmonics of that is 5th, 7th, 11th, and 13th order harmonics are eliminated. If you want to eliminate some other harmonics, right? If you want to eliminate that 17th order harmonic or 19th order harmonic, so you will get additional 2 equations. If you want to eliminate this 17th order harmonic, so that means you need to generate this H17 and H19. Okay, you need to generate H17 and H17 coefficient. Also, you need to make it 0. So what will happen in that case? You will get 7 equations. So when the equations number increases, right? So obviously the complexity also increases. So it is easy to solve up to these 5 equations. So beyond that, it is somewhat difficult. Okay, so normally at maximum we can eliminate these harmonics, and moreover, if you eliminate this 5th order harmonic, right, 7th, 11th, and 13th, so you can get a THD of around 5%. Okay, you can get a THD. For example, in this case, right, so this THD is roughly around 5%. So we have some inductance. For example, this is fed to an induction motor, right? The THD that can be usually in the range of 5% if it is connected to an induction motor. So machine is having some inductance, right? So that the inductions will be try to control, means try to reduce, means try to make it sinusoidal. Okay. Okay. So this is how to generate the firing angles, right? So these are the firing angles, all right? So for converter 1 means for H bridge 1, H bridge 2, HB3, 4, and 5, similarly, right? So in PWM scheme, we need to give, if you need to input this one, right? So after that, so this is the other angle is, so for example, this one, that means this pulse will start here. So this angle is 6.57. Pulse will continue here and this will stop here. So this angle is 180 degree minus, this is 6.57 degrees. 6.57 degrees. Okay. Good.
Sir,
So we
how,
understand. Yes. Yes.
how we will solve
How we
those
will solve
equations?
those equations?
By using different iterative methods are there, right? Newton-Raphson method or forward Euler method, you can solve these equations.
Okay, sir, by using MATLAB also we can do that.
MATLAB also you can solve these equations. Okay. Normally these are the non-linear transcendental equations, right? So these can be solved by using iterative method. So normally Newton-Raphson method can be used to solve this one, and moreover, whatever this is obtained, right? So this is for example, this is corresponding to MA equal to 0.8. Okay, so if you have different value of MA, so you will get different equations. So we already discussed when we discussed the selective harmonic elimination for 2 level, right? So when we discussed this, so this is the equations for a particular value of MA. So when MA changes, these equations or these angles also changes, right? So what we have to do is when you write a program for that, we need to solve for all the values of MA. For example, we'll solve for MA equal to 0, right? So 0.05 we'll solve it, and 0.01, 0.15, something like that. We have to solve all these things. So here you will get one set of angles. Here also you'll get one set of angles. Here also you will get one set of angles, right? So if you assume that the output voltage requires MA equal to 0.15, right? For example, for the inverter or for induction machine, if you operate for a certain load, right? See, it requires MA equal to 0.5. So corresponding to this MA equal to 0.5, it will pick up the required angles. Okay. For example, if it is MA equal, you stored MA equal to 0.1, and also you stored MA equal to 0.15, right? For example, if you want some intermediate value, for example, this is 0.17. So in that case, so corresponding this value, there is no output, right? That means you're not stored any angles corresponding to this, right? So in that case, using the there are some methods we can use that to, we can, that means we can, there are some methods, what are that methods are?
Is it extrapolation? Is it
Interpolation and
extrapolation?
extrapolation, by using interpolation and extrapolation, right? Okay, so we can obtain the corresponding values for any intermediate value. Okay, so that's why this, whatever this selective harmonic elimination, right? So this is very difficult in closed loop applications. In closed loop applications, this MA is constantly changing, right? So therefore, every time you need to look into that angles and you need to implement those, right? And moreover, once the angle is implemented, you cannot change in the one fundamental cycle, right? So if it's already turned on, right? So you need to wait until it's turned off. You cannot change this one, right? So whenever if you change this one, right, in that case, the dynamic performance is also implemented. That means you need to wait until one cycle is completed. In the next cycle, whatever changes are there, right? So that changes are implemented in the next cycle. This is same to the thyristor also, right? For example, thyristor is turned on, so we need to wait until the thyristor is extinguishes, right? The same thing here also. So that means you cannot change the modifications in in cycle. So whenever you done some modifications, you need to wait for the next modulating cycle to do the changes. Okay, so that's why it will affect the dynamic performance. This method is not generally preferred. So when we have the output voltage is constantly changing. Okay, so the advantage with this method is always it will operate at fundamental frequency. So that is the main advantage. Okay, right. So we already discussed that whenever this power, the power is not uniform, right? So in this case, for example, this is the battery, right? This battery is conducting for more period of time when compared to this one, right? That means this is overutilized, and this P5, or this is the power that produces this pulse, this is the out cascade edge bridge 5, that is underutilized. Okay, this is drawing less amount of power, so when compared to this one, right? So therefore, to equate that, we already discussed this in previous classes. So this is the pattern swapping. Okay, so this is the pattern swapping. So this is the first cycle. Okay, so up to here, so that is the first cycle. We'll follow this one, right? So we'll follow this one, and this is a subsequent cycle. So just we are changing the cycle. Okay, just we are trying to change the output voltage. So this is the P5, right? So now the P5 is comes here. Okay, so this is P5, P4, P3, P2, P1, and this is the another cycle. So we'll make sure that after 5 cycles, so every cascade edge page will produce same amount of output power. Yeah, so that means generally this P5 in the next cycle, so we'll swap this one. So from here, here, or here, here, and from here to here, something like this. Okay. Yeah, this already we discussed. So this is known as pattern swapping. So that means whatever the angle that calculates this theta1 is calculated for cascade H bridge, that means H bridge 1, right? Okay. In the next cycle, so this theta1 is goes to H bridge 2. In the subsequent cycle, it is goes to H bridge 3, and so on. So this is known as pattern swapping. This pattern swapping is useful to equate the power delivered by all the H bridges. So in this case, it will usually take n cycles. N is the number of H bridges in cascade. Okay. So you have any doubts on this? You have any doubts on this? You have any doubts on this?
No, sir. No, sir.
Okay. This is just extension of the selective harmonic elimination that we discussed for 2 level. So this is extension to higher level. So nothing, just is a direct extension. So next we will discuss hybrid PWM. So next we will discuss hybrid PWM. So this hybrid PWM, so use it to this is used to control the asymmetrical CHB. So this is preferred for asymmetrical CHB. So whatever the level shifted, phase shifted, we discussed, right? Level shifted PW and phase shifted PWM. So those are applicable for symmetrical cascade edge bridge. So in case of asymmetrical cascade edge bridge, that is, if one voltage is VDC, for example, one voltage is VDC, and another H bridge is fed from 2 VDC. So in that case, we prefer this hybrid PWM. Okay. So this hybrid PWM. Okay. So this is, for example, this is the output voltage that we require. Okay, so that is the output voltage, fundamental frequency, that is the fundamental component we required. This is simply so MA sine omega t. Okay, so this is the output voltage that you required. In case of this hybrid PWM, so what we have to do is, so we will split this one. This is the modulating signal. So we will split this into two different parts. We will split this one into two different parts. So one is, so we have two modules are there, right? One is operating, for example, this H bridge is operating with VDC, and another H bridge is operating with 2 VDC, right? So whatever the higher one, right, the 2 VDC one, so we will operate at the fundamental frequency. We will operate at the fundamental frequency. So like this. Okay. So whatever the rest of the things, the remaining thing is operated with this remaining. This is the output. That is what we require, right? So we already obtained the output. So with this lower, this means 2 VDC bridge, the remaining one, so that must be produced by the second H bridge. Okay, I think this one you can get more idea. Okay. So this is right. So this is the output voltage. Assume that this here we have VDC and you have 2 VDCs there, right? Okay. In this hybrid modulation, so you're supposed to get 7 levels, right? So in this, whatever or whichever having the highest voltage, so that will operate in the fundamental frequency. Okay, so that means 2 VDC1 is operating at the fundamental frequency. In this example, I took VDC as 10, so that means 2 VDC, that is 20 volts, and this is 10 volts, right? So this 20 volts is operating at fundamental frequency, so which is varying from plus 20 to minus 20. So whereas this 10 volts, so this is operating in PWM mode. So this is operating in fundamental mode, and this is operating in PWM mode. Clear? And this is the combined output. So this is output, this is 1 and 2. So this is the output voltage 1, and this is output voltage 2. Is clear? So how this is operating is, whatever having the highest voltage, so that is operating in fundamental frequency. Okay, the rest of the things are operating at PWM frequency. So this is in case of you have 1 and 2 H bridges. Okay, one is operating with VDC and another one operating with 2 VDC. So in case of multiple H bridges are there, in case of 3 H bridges are there, right? So here this one is operating at fundamental frequency, and rest of the two are operating at PWM frequency. Okay, so here this is one is operating at fundamental frequency, and here the two are operating with PWM frequency, and this is the output of this. So this is combined output shown in this. This is the combined output. Clear? So now the point is how to operate this in fundamental frequency. Okay. This is the output voltage that you required, or this is the modulating signal. Okay, so this is the modulating signal. So as already discussed, this modulating signal, so this is supposed to control VDC and the 2 VDC. That means 2 H bridges we need to control with this modulating signal. So in a first step, what we have to do is, so we will operate the second, whichever having highest H bridge, will operate and will obtain this quasi-square waveform. So this quasi-square waveform we will obtain, right? So we will obtain this quasi-square waveform, and this is the output voltage that we require, right? So we already obtained this output voltage. So whatever the remaining is there, right? So the remaining is, so this is 1, this is 2, right? And this waveform is 1 minus 2. Okay. That means this will be the modulating signal for the lower H bridge or VDC H bridge. Clear? So this is the modulating signal for the lower, or which are having the lower voltage H bridge. Clear? So this is the output voltage you required. So you'll produce a square wave within this output voltage. So within this, so you will obtain a maximum possible square wave voltage. Right. So here, next thing is we need to find out the modulating signal for the lower voltage H bridge. So for that, so just we subtract this one. Okay. So from this 1 and 2, if you subtract this, so this will be the modulating signal for the other H bridge. Okay. So if you combine this one, so you will get a sine wave. It's clear? Is it clear? Clear?
Modulating signal for the first one, sir. The first one, sir.
This one.
Modulating signal.
This one modulating signal. So this one modulating signal usually will operate in quasi square wave, right? So we operate in this quasi square waveform. So that means you have only one carrier, and we have the sine wave. So
Okay,
we
sir.
have one
Okay,
carrier
sir.
signal. So within that means 50 Hz carrier signal. So with that interaction, you will get this waveform. Or right, you can obtain or you can eliminate certain harmonics by using the selective harmonic elimination. So that we discussed. Okay. So your question is what is the angle of this one, right? That is your question, right?
Yes, sir. Yes, sir. Yes, sir. Yes, sir.
Okay. So this you can obtain in different ways. So one, using that selective harmonic elimination, you can eliminate certain harmonics. If you want to eliminate the fifth order harmonic or third order harmonic, if you want to eliminate the third order harmonics, this angle is 30 degrees, right? So usually this angle is 30 degrees. Okay. So that means this conduction period is 120 degrees. Clear? So usually this angle is 30 degrees. This
Yes, sir.
conduction
Okay.
period is
Yes, sir. Okay.
120 degrees. So this is the output voltage that you require. This is already we obtained. So whatever the rest of the things is, so that is the modulating signal for this. Okay. So here, this one. So this is the modulating signal. So this modulating signal, so we can control either one H bridge or the whatever the H bridges are left, right? So that is controlled by this modulating signal. It's clear? So this is the output voltage of the cascade H bridge 2, that is the VDC H bridge, and this is 2 VDC H bridge, right? So how this voltage is obtained? So how this voltage is obtained? By interacting the carrier signal with this modulating signal, right? The carrier signal. So with this modulating signal, you will get this kind of waveform. So if we add these two, this one and this one, if you add, right, you will get a waveform. So which is having 7 levels. So this is having 7 levels, right? 1, 2, 3, 4, 5, 6, 7. Clear? Clear? You have any doubts on this? The
Yes,
idea
sir.
is
Clear, sir.
simple. The first one, whatever, right? So whatever, this is the expected modulating signal is there, right? That is divided into two parts. So one that is operating square wave. So whatever the rest of the thing is there, right? That is the rest of the modulating signal. So that is used to control the lower H bridges or H bridges with lower voltages. The idea, yeah, similar here.
The
So this
same
is
modulating signal for all the lower bridges.
that is up to you. I will discuss it. Okay. You can keep the same modulating signal for all the lower devices, or you can use some other ways. So for example, this is VDC and 3 VDC. So this is the output voltage, which is 3 VDC, the highest one, right? So that is operating with fundamental frequency. Okay. Usually this angle is 30 degrees. Okay. right? And this one is operating at PWM frequency.
Sir,
So this is the
actually the
output
screen is
voltage.
not moving. Like we are stuck in the hybrid PWM output voltage slide.
Now it's visible.
No, sir, it's still in the same slide.
Now it is visible. No. Now it's visible or no?
No, sir.
Now you're supposed to see 9-level asymmetric CHB inverter as title.
No, sir, it is
No,
not
sir.
there.
It's not there. Now it's visible.
Yes, sir.
Yes, sir.
Now it is visible.
Yes, sir.
Right. So this is, for example, this is, we have VDC and 3 VDC is there, right? You're supposed to get 9 labels, right? Starting from 4 VDC to minus 4 VDC. So this is the output voltage of the highest rating H bridge. So as usual, will operate at the fundamental frequency so that it is a quasi square waveform, right? So this is the output voltage of the lower one, that is VDC one. This is the output voltage of this one, and this is the output voltage of this. Right. So this is the combined output, so which is varying from 4 EDC to minus 4 EDC. Right. So your question is, right? So you have different ways are there, right? So you have, this is 2, right? In case of 2, so obviously the first one will operate at square wave, which is having the highest rating, and second one you have only one bridge, right? So that means that is operate with whatever the rest of the modulating signal, that is a subtracting between the original modulating signal and the square wave. So that is the modulating signal for the second one. Okay, so there is no confusion. So now the question is, one, if you have 3, 1, 2, 3, right? So in that case, the first one is as usual, is operating at the square wave, right? And remaining 2 and 3, right? So remaining 2 and 3, we can operate with remaining modulating signal. That means 2 and 3 can be operating with the remaining modulating signal, or right, or we have this one, right? So this is the original one, right? So this is the original output voltage that is required. So one first N cell is operated. So N cell is operated, and this is the output voltage that produced by the N cell. Okay, the output voltage that produced by the N cell, and this is the subtraction of, this is the original modulating signal or the required modulating signal, and this is the output voltage of nth modulation, and this is the modulation for the n-1 cell. Clear? So this is the modulating signal for the n-1 cell. So that means after that we can have this is the output voltage of n-1 cell, right? N-1 cell, and this is the output voltage for the first one or the remaining one. So meaning is simple. If you have 3 H bridges are there, right? The first one is operating at the fundamental frequency, right? Second one is operating with the remaining fundamental, means it is operating with a fundamental frequency with the remaining or without the, with the subtracted modulating signal, and third one is subtracted modulating signal. So that means meaning is if F is the modulating signal for the original one, the first one modulating signal is a square wave, right? And the second one modulating signal is this, what, this minus this. So this output voltage minus this output voltage, and the third one is, so this is you got some square wave. This is one, for example, this is square wave 2. The third one modulating signal is the original sine wave minus the square wave 1 and minus the square wave 2. So that means original fundamental minus square wave 1 minus square the square wave 2. Okay. So that means this is quite common if you have VDC, for example, and you have 2 VDCs there and 4 VDCs there, right? So that means this VDC is operating at fundamental frequency with the remaining modulating signal. So this 2 VDC is operating. So with that combined remaining, so this VDC is operating. This picture is explanatory, right? This first one is operating. So it remaining modulating signal. The second one is operating. So this will continue, and this is the last one is operating with. So whatever that remains, and we are adding the outputs of all H bridges, and this is the combined output. And this is the combined output. Yeah. Right. In this case, there are two scenarios. So this is anyway for cascade H bridge case. So you'll always get even odd number of levels. So for example, if it is used for some other methods that we will discuss in the later classes, if you have even number of levels, in some cases you have even number of levels, that is 4 level, 5 level, 5 levels, 4 level, 6 level, and so on. Right? And we have odd number of levels. So in case of right, in case of odd number of levels, right? So usually we need to start like this. In case of odd number of levels, right? So why odd number of levels? In case of odd number of levels, we will generate 0 level, right? In case of odd number, we will generate 0 level. In case of even level, we cannot generate 0 level, right? So this is in case of even number of levels. In that case, you cannot get a 0 level. It looks like it is 0, but this level is actually changing from this value to here to here. So this level is changing from here to here. So there is no 0 level here. So this is how the pulse square waves so that are placed. We have some different levels. In case of odd level, so this is we need to follow. In case of even level, so it must be start from the origin so that the waveforms will be more symmetrical. Okay, so this much details are enough. I don't want to go deep into this. So only thing you need to remember that in case of hybrid PWM, so whatever the output voltage, so that obtained from the highest voltage bridge, right? Means whatever the output voltage means the control the lower voltage H bridges. So we need to subtract from the actual reference voltage. That you need to just remember. So there is some drawback with this this hybrid PWM, right? Since the modulating signal is not a sinusoidal, right? The modulating signal is something like this, right? So here this modulating signal is something like this, right? Because this is the remaining one, right? So here the drawback here, this waveform is moving from here and here, right? So in this particular case, that means the conduction periods are very less. So therefore, you will get some glitches like this. So this is some unwanted switching. So here also some unwanted switchings. So these are the unwanted switchings because of some narrow pulse pattern or this narrow switching, that's a narrow interaction of the carrier and modulating signals. So this is the drawback with this hybrid PWM. Okay, it's clear. If you have any, ask me. Any doubts on this? You have any doubts on this? Okay, if you have no doubts, I will stop here. So with this, we are completed the PWM techniques for this multi-level inverters. So maybe in the next class, we will discuss selective hormone or space vector modulation technique.